Okay, this is the machines recitation. Fab 1.0 is you buy a Fab Lab. Fab 2.0 is you make a Fab Lab. And waiting further out is 3.0 is assemblers and 4.0 is self-assembly. Not quite ready for a recitation on that. So, but we've got a dream team of machine builders to cover the Fab 2.0 transition. I'm at machines.fabcloud.io. Right now, it's just a page of links, but the intention is to tend this as a portal into the machine building. And this is a table of contents. In the Fab Academy class, we're going to do this recitation. Then class on Wednesday is going to be all about machine building. Then you're going to spend 2 weeks on a machine building assignment. So this is kicking that off. You know, at the end of which you should feel like you can create your own machines. So there won't be enough time for any one of these in enough detail, but we're going to spend roughly 5 minutes a person. Some need a bit more than that, some less. Touring who's doing what, each will take over the screen. Now, the first link is Nadia, who I don't see in. It is 6 o'clock in Seattle, but she did a thesis on object-oriented hardware that really helped kick off the idea of Fab Labs making Fab Lab machines. She's made a series of interesting early Fab Lab machines linked through the MTM site, and is now running a machine building, well, more than that, but a group at the University of Washington. So we'll hear from Nadia if she appears. She helped introduce the idea of machine building. Then Jens picked up from her. So Jens, take over.
All right. I'm a former Fab Lab nomad and an independent researcher and industrial designer, and a co-founder of a Fab Lab here in Oslo called Fellesverkstedet. And I started an informal research project called Fabricatable Machines. So 1 second, I'm going to share my screen. So the third link here, Fabricatable Machines, to the wiki. This is the homepage of our of the project, or former homepage. And what we looked at with fabricatable machines is how can you make as many ingredients as possible of your own machine. So really sort of taking it to the extreme, making your own rack and pinion or drive system and axis from scratch, for good and bad. And we've been sort of exploring that, sort of what are the consequences when you make such large degree of your own parts. And it is of course very difficult to make high quality machines that stay high quality for a long time when you make a lot of your own components, but it also gives a lot of freedom and sort of insights. So you can see here sort of an example of an earlier machine where the self-made parts on the right and then store-bought parts on the left, and sort of everything optimized for digital fabrication. And with fabricatable, we mean that something can be fabricated by another person without too much prior experience, that it makes it more easy, for other people to make. So we make sure that you don't need too advanced techniques, sort of avoid two-sided milling or advanced milling, for instance, and also try to source components that are easy for other people to source around the world. And if you go to the machine family in the wiki, you can see all the old machines. There's currently only one refined, sort of recommended for reproduction machine, and then there's a whole list of retired machines. This is Humphrey 1, for instance. I'll show you Humphrey 2 later, and a wood version of that, which was naughty and fun, a complete wood machine and so on. This one I liked a lot, this screen printed 3D printer. And we also have some publications if you want. I've been working together with a PhD student and with guidance from Nadia as well. So Frick Fosdal has been doing the heavy lifting on making some formalized papers on our work, and we just got a second paper published last year, which I'll link as well. So we focused for a long time on building the existing type of we thought if you can replicate the classics, then then it's proof that you're ready to build new machines. And Hanso is a research platform that I built for my own studio. So this is a bit of an exotic architecture machine that I built in order to be able to experiment and test out different ideas. It's actually designed in FreeCAD. So I open source software to make the machine. We made all the parts on the Shopbot, and here's some assembly. And here we use it for making new machines. And I just made this little overview here. So here you can see the current machine, sort of the generations. First, we used a Shopbot or multiple Shopbots to make Hanso, and then Hanso, my own research platform machine, I used that one to prototype the first version of Humphrey 2, sort of like a classic CNC router with sort of equivalent performance of Shopbots and other CNC routers. And that CNC router was precise enough to be able to copy itself. So it's designed to be able to make all its own parts, which we assemble now just before Christmas. And here you can see a little test of precision. So I don't know if you're familiar with this PCB milling test. I actually milled this one together with Neil before Christmas, and you can see here that the feature size that this 2.5 meter long work area machine could make is quite impressive. So I think you could actually take Fab Academy with this machine. You could do all the electronics homework on this machine, which is kind of fun.
1 minute warning, Jens.
All right. So I have prepared a little demo, so I'm going to stop sharing my screen, and then I'm going to run a little macro here. So I don't know if you can hear the sounds, but you should be able to see it.
We see it moving behind you and hear it.
So here you have the milling head with the dust extraction, and then there's a print head here. This is regular FDM printing. It's powerful enough to carry around its own spool of filament. But then also you'll learn later of Jake's works with tool changing. So I'm preparing to downloaded his files to add a better hot swap solution to be able to go faster between printing and milling. In progress, we have a pellet extruder that's going to go onto the machine. That's why it's so heavy, but this pellet extruder is not working well yet. Okay, anything else, Jens? Then we're going to go on. Yeah, I think I should just quickly show the CAD file for Humphrey. So if you download, you can see this is maybe the most relevant machine for the class. This is designed in FreeCAD, and as you can see here, it actually, while I designed it, I made sure that all the parts fit on one cut sheet. So feel free to have a look at that in the repo. Good. And there's of course more to say, but that's enough for now. Thank you. Great, thank you, Jens. Then Nadia, I introduced you. If you want, you can take over, or we could also end with you. Either way. Why don't you go on? I just did a quick intro to, I clicked on your thesis in MTM, but why don't you take over and pick up?
Hello, everybody. I was formerly in the Center for Bits and Atoms, and now I run my own lab at the University of Washington called Machine Agency, where we focus on harnessing the precision of machines for the creativity of individuals. Here's some of our research. I was going to show you a few things, maybe a little bit more in depth. This is sort of work that I did in Neil's lab, where we were exploring what it might really look like to have personal fabrication or portable fabrication. This is a project I did with Alon Moyer in 2010, where we were exploring what it might be like to have a machine that was kind of like a laptop rather than a mainframe computer. And then with James Coleman, I spent a whole series of explorations on exploring what it also might mean to break machines down into respective components that you could then assemble and reassemble and change and configure. So modular machines that you could make to do different things. And in my lab now, one of the machines that we use a lot for that embodies these kinds of principles is the Jubilee machine, which is fabricatable, to borrow a word from Jens et al. And meaning you can build it with off-the-shelf parts and with things that you can make in a fab lab. But it allows for tool changing and therefore you can pick up and drop off different end mills, different end effectors, microscopes, etc. Here's the website for Jubilee. You can get kits for Jubilee now, but you can also just make them all yourself. And I think probably by far the most popular application for Jubilee is multi-material 3D printing. So sometimes multi-material is as simple as multicolor. But in my lab, we increasingly explore the possibilities of multi-tool workflows. So if you wanted to, for example, build clinical analysis workflows, if you wanted to, for example, see what was going on in a blood stain or in a bacterial colony, or this is currently one that's very popular in my lab. What can you do with machines and plants? Perhaps some of you are familiar with duckweed, the plant that floats on sweet bodies of water. And this is a Jubilee that is outfit with tools. So like PopFab, Jubilee has a kinematic mount that allows you for picking up and dropping off these tools very precisely. And so here are a bunch of different Jubilee tools that we're using to manipulate duckweed, this small green plant that grows on the surface of ponds. So inoculation loop that we use for picking up and dropping off the duckweed, syringe, which we can use for feeding the duckweed, cameras in different directions for looking at the duckweed, and also other syringes for perhaps manipulating the duckweed more intimately. And by having all of these in the same machine, we can program them to do like these more complicated workflows, like picking them up and dropping them off to do different kinds of growth over time experiments. We also have adapted the Opentron's pipette head to the Jubilee. And one of the things that I guess all of this machine building has led to is understanding what are the different ways in which we can control these machines, or what are ways in which it's actually easy to do all these different things. So a lot of the machines that you use in the Fab Lab, you control with a variety of flavors of G-code. And how you generate the G-code is maybe through a slicer or through a CAM program. But for a workflow like this, you actually end up having to do a lot more complicated, or not complicated, but you have to do a bunch of sort of disparate commands, and how do you accommodate that? And so here, this is a Jupyter notebook that we're using to control the machine. And so how can you make sort of programming the machine a easy and iterative process, same way that you might do with prototyping. And so here you see the communication with the machine is easy enough for someone who maybe isn't a programmer to still understand, okay, here we're going to change tools to the media syringe. We can move to different locations on the bed plate. We can dispense 20 milliliters of liquid, and then we can perhaps go somewhere else and dispense more liquid. So how can you create kind of the scripting environment where it's like scripting with machines instead of having to like generate all the code ahead of time and then running it all in one go. Similar, this is work from my student Blair Suraman. He created an extension to the popular language p5.js. I don't know if you guys are all familiar with writing and processing. P5.js is a JavaScript version of it, and allows you to write strange tool paths directly from p5.js so that you can start exploring doing kind of weird things with printers, like printing on uneven surfaces or creating strange toolpaths. Another one of my students, Jasper Channer O'Leary, has been exploring machine control, not from Jupyter notebooks, but from observable notebooks. So observable notebooks is a JavaScript computational notebook environment. And he's specifically doing it for CNC milling. And so here are some examples of little widgets that you can see on the left. Here's like a widget that he's created in observable in JavaScript to be able to design a shelf, for example, which he then can use to directly control the shopbot. And then we have an overlay. We have an overlay that's projected onto the shopbot so that you can also see what the machine is planning to do. So we have a projector mounted above the machine that allows you to also understand how do these things that are in the computational notebook translate to this physical world and vice versa.
Nadia, 1 minute warning.
Yeah, and then last project, this is another programming environment for machines. This one is by Hannah Twigg-Smith. And she's created a browser-based workflow environment that is modular and extensible. Here, for example, is a module that's controlling the AxiDraw, plotter. And she's created this way in which you can have this correspondence between directly what's happening in your online canvas and the machine. And that kind of rapid iteration of like creating the control software and being able to execute it quickly lets us do lots of really rapid explorations of what different toolpaths might have as real material outcomes. So she's extensively worked with the plotter Twitter community. And here she is, for example, using a plotter not to plot with a pen, but to explore what different brush strokes end up looking like. It's one thing to see what the toolpath is, but it's a very different final visual result. So yeah, that's perhaps like a tour of what we've been up to. If you would like to know more, my email address is nadia@uw.edu.
Okay. Thank you, Nadia, and thank you for getting up at 6 a.m.
Oh yeah, no problem.
So Nadia helped introduce machine building. Jens really tackled machines that are good enough to make their own parts. And then Danielle and Gracia began as a Fab Academy student, turned Fab Academy instructor. And I think there's a machine building gene, and Danielle maybe has a few of them. Let's see, Jens and Danielle both recently visited with SolidWorks. We've been working with them where they've been donating labs, and the most recent one going to Haiti is a lab made in a lab. That was the machine Jens said. And so Danielle is really run with how you make all the machines and then how you document them and how you back them up with supply chain. So Danielle.
Thanks a lot. I will just share my screen. Okay. All right. So in this presentation, we are going to show the Open Lab Starter Kit, which is actually our current research program. And we are currently streaming from InMachines, which is a limited liability company focused on building open source machinery for Fab Labs. So we recently enlarged our team that now counts all these people you see on the screen, including Raul, which will stream his presentation from the office. And so our goal is to make the full inventory of open source digital fabrication machines that Fab Lab could use. And this means that all the machines should have accessible design, that there should be a lot of transfer of the knowledge with workshops and research, and all the machines should be also something that people can replicate locally. So we are currently just above the first year of the project, which consists of 3 years, and we have been just delivered the full Open Lab Starter Kit to our clients. So part of the research is about workshops. So here you can see some pictures about people building a lot of different machines. This is a laser cutter machine, then a large format laser cutter, They're building a CNC machine. Yeah, and all the machines have been published already on the links you find on the schedule on GitHub. So, and yeah, so before we were doing the documentation in a very simplified way, IKEA style, let's call them PDF manual, where there was an exhaustive guide on how to replicate all the machines. But this guide was too monolithic because it was based on a PDF. And therefore, we needed to do a lot of work to modify it. And it was also based on a lot of manual work. So right now, we are shifted to an assembly manual, which shows the 3D view of the assembly. And this is automatically generated from spreadsheets and a set of CAD source files. So just change the file and change the spreadsheet, and this will automatically generate a new assembly manual. In the assembly manual, there are also animations about exploded views, or for example, part highlighting where you can see what parts is going to be assembled in this step, what parts in the next step. And especially this system will be compatible with any CAD file format. So you just change the files and then it will load it automatically. So we have already been presenting some machines. I think this is a small laser cutter deployed in more than 20 schools. The bill of material is around 2,000 euros. This is a small format CNC milling machines with a vacuum table, which has a bill of material between 2,000 and 3,000 euros. This is a large format laser cutter that have been built also for the Open Lab starter kits. It's the first machine we can produce both in the lab. So if you have a shop, but you can CNC mill the housing and everything, but you can also, for the first time, produce it outside in outsourcing. So if you ask a company that has laser cutting machines, you can easily produce multiple of these very quickly. So, and this was also a large format 3D printer we presented the last time. It's a 1 cubic meter 3D printer that can print up to 1 millimeter layer height with a custom heating block that we have been doing here in the company. So the current Open Lab starter kit machines are the following. So the first one is an open source 3D scanner based on photogrammetry. And the scanner is super compact. It has a bill of material, which is around about 130 euros. And it can produce results in photogrammetry. Here you can see an input and output of the results. And we plan to deploy this kind of scanner in schools because the simple construction and the cheap price. So then we also made a small format 3D printer, which is completely made of snap fit aluminum frame. This one is still a little bit more expensive, but it has touch screen, auto bed leveling, and it's reaching a very high quality print for the first version. So then we also made a large format CNC milling machine, which is the size of the Showbot. This machine has a bill of material which is less than 5,000 euros and uses a mix of standard aluminum profiles, steel pipes, and CNC milled parts in the fab lab. So the steel pipes are just cut to size and then drilled. So you don't need to CNC mill hard metal for it. And then all the parts are easy to square and put together. So here you can see some examples. Yeah. So we also made a open source vinyl cutter. And this is a very small machine. Bill of material is around 130 euros, 120 euros. And yeah, it's a portable one. It's based mainly on 3D printing and using inserts on the 3D print and use a solenoid in the head to work with the files. So as you can see here, and you can regulate the power by changing the current on the solenoid, but you can also change the heads because you can put a pen or a knife or some other tools. So, and we also built a machine in Baltam. Here you can see some pictures. So this machine is already an improvement to the previous one because in the previous one we had more than 800 screws. This machine has only 160, which is still a lot for us, but it's a huge improvement for us. Laser calibration takes less than 1 hour to be built, and it's compatible with all the voltages. So Neil, we are gonna do a small live demo of the machines that are here around. So I will just mute here.
Okay.
So I'll stop sharing. All right, can you see?
Yes.
Perfect, okay. So this is our larger format CNC machine. I think we can run a small demo for it. Alberto is running a G code in the air. Let me just show some details for the machine. So the machine is also quite special because it has a very high z-axis that we can use to mill molds. And it's also without the bed, so you can just put a piece of MDF in the bottom to cut your jobs. Yeah, and it uses pretty much standard material. This was surprisingly the fastest machines that we have built. So it took less than 1 month to design it and prototype it. So the second machines are here. There is here the small format milling machine, which is not operative at the moment, but I think Raul already milled some nice keychains with it, and you can mill PCB and the vacuum for it. So you can attach the vacuum with the MDF plate and then mill PCBs. So then we have the large format CNC machine. Yeah, okay. Which I think here, can look at it. Yeah. All right. So let's go next to here there is a 3D printer. Okay. Which is printing this large vase. Okay, so here is the laser cutter, the small format laser cutter over here. Yeah. Then the 3D scanner. Yeah, the 3D printer, which is currently printing. And last but not least, the vinyl cutter. Yeah, I think we can show the large format the laser cutter printing maybe. Right. Yeah, some demos. So with this machine, you can cut 20mm wood. Yeah.
So Danielle.
All right, I think we are done with the live demo. I can go back to the computer, unless you have questions here.
No, it's fabulous, very impressive. Talk about your experience fielding a lab with these machines, a Fab 2.0 lab.
Yeah, so I think, so we structured the project in machines that have 3 versions, so we have to make 24 machines, but like every 2 weeks or 1 month, a new machine comes out. So our experience is that we are quite mature on the laser cutter side, so we can make machines that, according to people in Nashville, it didn't look like a Fab Lab made machine or an open source machine. It looked like a commercial machine. And our customers are happy. We can make more. We have more than 20 schools using this machinery here. But of course, the new machines, for example, large format CNC machine, the vinyl cutter, for example, they still need quite some knowledge to be run. So we wait at the end of the project of the third year to have mature enough machines. So if you are a Fab Lab and you have enough knowledge, for example, let's say a Fab Academy graduate, then you can use all these machines. But if you are someone from outside, they're still requiring some knowledge to use them.
Okay. Good. We could spend the whole hour with you there, but we're going to need to go on. So fabulous work to you and the whole team. Congratulations.
Thanks a lot, Neil. Here is the team.
Well done, all of you. Okay. So next we're going to go on to Jake. So Danielle, if you stop, let's see, there's no screen share. So Jake, if you take over, Jake then took over roughly from Nadia and really descending into the controls. If one person is making and using the machine, what does that change about the whole pathway from CAD, CAM, machine control, motion control? So Jake, and then as Jake talks, we'll pull in Quentin and Leo.
Yeah, so I think I was going to speak mostly about Clank now, and then Leo's going to talk about modular things, which is sort of the latest in incantation of all the controls work. But I'll do a little bit here. So yeah, awesome to see everyone else's work as well. And in Nadia's lab, there was a tool changing machine. And we have also Clank, which is sort of similar spirit, which is sort of one machine to rule them all. And it's entirely 3D printed. So it's also fabricatable, I think, which is a word that Jens invented, which is quite fun to say. I don't know if it's a real word yet, but so the bill of materials for Clank is about $350. You only need a 3D printer. It's the only like tool you need, and then a set of Allen keys, and then everything else is off the shelf. And so now that you can buy a 3D printer for about $300, you can sort of kickstart your whole lab for about $1,000. And the dream, of course, is to have one motion platform and a bunch of different tools. So Clank more or less realizes that. We have two versions. This is a little Core XY version for sort of flat shaped jobs. So sheet material processing, stuff like that. We've also done sort of semi pick and place work with it. So this was a internal project at CBA, trying to make things out of other littler things, which is a classic CBA adventure, where we quickly turned Clank into a little pick and place machine. So here it is placing two of these little tiles, and then it switches tools to use to pick up these little H things back here. Anyways, that's the Core XY version. CAD for these are available just directly in the page, which has been an awesome little tool to use as well. You can open this up down here in Fusion if you want to poke around the designs. This is the sort of the other Clank. This is for things that are more volumetric in aspect. So 3D printing, milling, stuff like that, but using the same tool changer. This one's a little bit less developed, but it works the same. And this is all based on this tool changer. So this is entirely 3D printed. The contact points in the kinematic mount are all just off the shelf hardware. So they're like button head cap screws and socket head cap screws. And it's lever actuated with a sort of over center lever thing. And when we tested this, the repeatability of the tool changer was down to about 6 microns. This is a slightly bigger version, or yeah, better view. And so, oh, and then of course, the trouble once you get into tool changing is putting a new tool in your machine sort of implies a new controller as well, which is tricky because normally we make controllers out of pretty monolithic systems. So this is an early prototype of a little pogo pin connector. So you can see right here in this blurry video, this little circuit basically just passes USB-C through from the tool to the or from the machine to the tool. And we'll talk later about some modular systems for building to describe those controllers. And then here's just a bunch of tools. So this is a pen plotter that has RGB and CMYK, and a little rotary axis to turn them around. This was just a calibration step. The CAD for these tools is also available on these websites. This was a rotary tool that we put a little rotary knife on to cut paper airplanes with. This is a 3D printing extruder that has also a bunch of instrumentation on it. So we're working on a project with NIST to measure the materials that the printer is using while the printer is using them. That's what this is for. And then I think last year, Alfonso, who's another student of the CBA, sort of unceremoniously slapped a Makita router onto a Clank. And it functioned pretty well, actually, as a sort of surprise shopbot. And I think actually his dad currently has one of these in his garage shop doing shopbot stuff. And then this was something we did at a Haystack, I think last year. There's been a few incantations of this as well, but this is I call it a mud stick. It's a thing for pushing clay out of a nozzle. And this is a common thing that it seems like it's actually quite difficult to design in the open source. So this design, of course, I love it. It's available and stuff on whatever machine you'd like. And then, yeah, for controls, so I've recently woken this project up again. This is a stepper motor, but it's controlled in closed loop. And so you can see in the top left here, as I'm exerting a little bit of force on the motor, it's reading out the effort that it's using to control position. And especially with newer motion control work we've done for modular things, we now have a really good framework to start integrating this kind of learned like motor models into motion control models. So actually just this week, I've been playing with this again to see if we can build automatically torque curves for motors. Here it is positioning in closed loop. And then use those torque curves in our acceleration controllers. So rather than like right now in machines, I'm not sure if anyone's done this, but when you tune the acceleration, it's just a sort of one value. You know, there's maximum acceleration, maximum speed. There's actually a much more rich model underneath that we can expose. So that's worked in that direction. And then I think sort of most importantly for this group especially is starting to think about interfaces. So if you look at open source software, almost nobody writes everything. Individual contributors make small contributions of modules that other people use. And in machine building, it seems like we're sort of stuck in a world where groups who develop and build machines have to do sort of more or less the whole stack, mechanical design through to electrical design. And so it's really interesting, and we'll talk more about this when we talk about modular things, is this idea that little, groups of us could develop little parts of machines that we could all share openly without having to get so much into the guts of everything together. So anyways, this is just a nod at the modular controllers stuff that I've done. This is the printer, and I think there's 14 different modules on here. There's a bus to connect them all. I think that was what I had.
That's great. And as we go on, the key transition is the prior machines you saw generally all had a centralized controller that embeds state. And so if you change something in the machine, you have to change something in this controller between it and the outside world. What Jake showed are distributed controllers. And so maybe go to Leo and then to Quentin.
That would be the most logical, order of.
So
sure.
Leo, take over.
Sure. Okay, yeah, so showing distributed controllers. So
Jake, stop sharing. Yeah.
And I can start sharing. Let's see. So can you see my screen? Yeah.
Yep.
Great. So last fall, Jake and Quentin and I got together and we wanted to make these tools that we've all been working on, and Jake especially, for a couple of years, available to people in an accessible way. So we started building out this modular things project. And basically what it is it's tools for making modular hardware systems that you can put together in software. So the core parts of it are this networking library, which Jake built, which is, he didn't reference explicitly, but it has been called OSAP, maybe called something else in the future. And basically it's a tool for routing messages across devices. So you can put it into a device, an embedded like firmware that you make, and then a web-based editor for actually putting those devices together into a coherent functional system. So here's an example. Well, here's a collection of circuits that we made with modular things that we provided to the Fab class in the fall. How to make almost anything. So that's the section at MIT. And they used it to build machines. And I'll show a little demo that we made for Kai. So here you see the editor. This is an early version of it. And as Jake plugs in a device, that device pops up in the browser. And it also describes like what it does, how to use it, what its API is. Then he writes a little bit of glue code to take these two devices, which is a potentiometer and a servo. And now you can see that just that little bit of JavaScript has connected them. So when he turns the potentiometer, it's actually doing something. And because he's in a browser, he can also write some HTML, CSS, and JavaScript and make a little interface for it. So we built some more involved machines, like the xylophone that I showed. Here's all of the code for describing that machine in a single file. And then here's an interface that's also described in that file. It's a sequencer that will control the machine in real time. And we gave these to a bunch of people who have the same task as you in the next week, and they used it to build all these machines. And most of them had about the same experience as you as well. So here's a pancake printer. You saw the Core XY machine. It was like 4 different machines. So that's a quick overview of the project. The current state of things is the editor's been updated. It's kind of hard to see probably what I'm doing, but this is basically the same demo that I showed in the video. And you can see that if I unplug and replug this device, then it comes up, and it's got an interface as well. So now I'm turning a dial here, and everything that you need to describe this is just this file right here. I work at an edtech nonprofit called Hack Club, and we're using modular things as the underlying platform for building like a gateway digital fabrication machine, which is this small drawing machine that we'll distribute in the fall. All of this is open source too and available. So if you're interested in just like a basic machine design that's cheap, you can check this out. And that, Quentin or Jake, do you guys want to add anything to that?
Yeah, so I say let's go on to Quentin now. So thank you, Leo. And then to lead into Quentin, for machine building, I've been interested in how far it can be simplified. So there's a lot of software and some non-trivial hardware supply chains. And so I was interested in how far you could simplify both the software and the hardware. So Quentin, take over.
Yep. Oh, those are spoilers. Let's see. So that was a good intro. You've seen pretty complex systems now. Let's look at the most basic thing you could do. And this started all the way back in the Carolina bootcamp in early 2020. And the name of the project is Urumbu because in that region, that's the name of a small ant. And the idea is in this project, the electronics is as simple as it gets, but together you can make a more involved system. So it started during that bootcamp, and then it took 1 more year to make this basic stepper. It's a USB device, and there's a D11C there because that's our favorite USB capable chip, less than $1, at least back then. And Neil showed that you can drive 4 of them simultaneously simply by streaming bytes from a Python process. So those nodes don't even know that they're part of a machine. They just get those bytes and execute 1 step per instruction. The code is as basic as it gets. Let's see here. You just get a byte that's either a F for forward or a R for reverse, and you execute 1 step. That's it. That's the electronics. We made more modules of the sort. There's a portal, sorry. Right here. So you have all those input devices, capacitive sensing, distance. This ADC could be used for a thermometer, for instance. Here's a potentiometer, and then output modules. I showed you the stepper. This is a servo, and here is just a transistor if you want to turn something on or off. So for each of them, you can just click on the link. You have the board, and the code is always very basic, I promise. It's just this. For an input device, you would send a question mark. You get 2 bytes. That's the value. That's it. Now you need a machine to test that on. So 1 year ago, we got together. It was my first time in the US, actually. And in just 4 days, we managed to build this machine, which was a very basic drawing machine using only a string for transmitting the motion. And here's a test of the precision right here. So this was kind of a surprise to us that we could drive this whole thing from a Python process. Every single step that every motor is taking is 1 byte being sent by the Python process. The code is also available here if you want to have a look. It's Python, but really it could be any other language as long as you can send those bytes. And this is where this system that Yanni and Fran just developed is quite interesting because you can now do it from mods. If you go in modules, right at the bottom, there are two new modules called Rumbu and Rumbu Movement. And the idea is just that you would add this Rumbu module, connect a device. I don't have one right here, sorry for that. But then as long as you can transmit letters to this node, then it's gonna just forward them to the Rumbu module. So the idea, and this is still experimental, but there's this Rumbu movement node that can send steps to 7 modules. So you would select a text file with a bunch of X or Y characters. You know, a capital letter is a forward motion, a small letter is backward motion, I believe. And then this can stream X commands or Y commands. This node is just to debug it. I see a bunch of F and R's being sent to the X motor in this example, and it would drive the machine just like that. So as long as you can produce those characters, you would have a machine that moves. Okay, so that was very brief, but that's the software side. Then if you want to take a look at the hardware, those are 2 more iterations on that. This one is a fully printed axis, again with the string for transmitting motion.
The string.
The string is a replacement for a timing belt. It's very cheap, and it's a special low stretch string. I think it's from fishing lines, right?
It's Kevlar. It turns out there's a military specification for Kevlar string that is very low stretch.
Mm-hmm. You can also use steel cables. We also have tried that. It's even less stretch. And so you have this capstan that generates friction to mate the string and the motor shaft. And this whole axis is 3D printed on a Prusa. I made it as long as it would fit on the bed. It prints in one go, and then you have the carriage with a flexure to make sure the wheels always have adequate contact on this beam. And here is the thing moving. And remember, this whole acceleration profile is generated by Python code. The machine doesn't know anything about it. And then a more involved kit that you can try to use is this one. The carriage is a bit more involved. You can see the flexure is slightly better designed here. And it's a kit. So you have all those attachments that you can put at the end of a beam. This one is just a single linear axis, but if you want to add beams on the sides, then you have all those joinery parts. And yeah, that's about it. It's all design diffusion, but there are step files as well. So just go and have a look. I promise it's fun.
Okay, great. Thank you, Quentin. Then an interesting trend has been the emergence of super fab labs with more advanced machines to make the parts of the machines. One started in Kerala, another one in Bhutan, and that's helped drive machine builders. So Rahul came from Kerala. So go ahead, Rahul.
Yes, hi Neil and everybody, good day. So my name is Rahul, I'm from Kerala, and I've been working on a very small project called the Pico. So what it is an entirely 3D printed CNC milling machine, which you can print inside the Prusa. So it has some unique features like a flexure Z-axis and a friction drive spindle. So I've made the entire machine to be under $250 US so that anybody in the lab can make it. And it is a PCB mill. So it is a core technology to have. Then, so here, if you go to the docs, so these are all the repository for it. Okay, so this is an iterative process. So for the first project, I actually started with PCB mill because in order to simplify the machine building for PCB, you only need 2 accurate heights. One is to mill out the traces and one is to mill out the board. So I started the first project with the flexure designed like this. So this is a combination Z-axis. It has both the flexure for the axis as well as a means to move it. So I'm using a camera to move it. This is the first 3D printed version. This survived about 2 minutes. After that, it broke. Then I tried various iterations. So this is from PLA, HDPE, Delrin. So these are different iterations of different designs and different materials. And this is the first successful one, which lasted more than a minute. That is on the machine. And in order to make things easier, So I designed some plain bearings instead of using the linear recirculating bearings. So these are very easy. You can build them directly using Delrin. Then the machine frame is a simple design. You can mill it out on the shop board. These are all flat panels. You assemble them together. It's a two-part design, x-axis in one stage, y-axis in the other stage. So fabrication is really easy. Everything fits in 80 by 125. And this is the Zund milling out the z-axis. Then for the first spindle, I used an old Modella spindle I had. And this is a full machine. And so this is the machine working for the first time. Here you can see the z-axis moving in a very gradual way. It works, but it had some problems mainly because of rigidity. I had to optimize the design of the z-axis more. So I did some simulations in Fusion to find out the stresses involved, how long it will last, how I can improve it, like the fatigue. So with that, I came to the second version. So this is mainly a focus on rigidity. The first one had a problem with rigidity, so you won't get very small traces. So here I used really hard materials like phenolic laminates. I changed the Delring into Delring bushes, which you can mill out and stick it into the design. So these are very easy to make. And these are the parts made out of phenolic laminates. For testing, this was the first successful one with really good results, but it was super hard to make. The phenolic laminates milling is very difficult, at least for me. So while I was working on this, Sibu, one of my instructors, came and told me, why don't we 3D print the whole design since it is very small? So then comes the Pico. So we 3D print the design. This here you can see the entire model here. So it's very simple. So what you do is that in the x-axis, you take the whole thing, you take all the precision assembly parts, and you print it out in one step. So this is very easy to print. It takes a total of 30 to 35 hours, and it fits in a Prusa bed. So the assembly is also very easy. And for testing, here you can see the first result with 3D printed. So it uses 3D printed parts, but it also has an acrylic backplate, which gives it the rigidity. So that's a bed for, and this is, and I included another one. So this is the final version right now. It's a V2. So this is a Pico V2. It has a cover, and here the fabrication side. This is a full design. You can download it. You can print it. Here you can see the backplate. There's an acrylic panel here. This is what gives it the rigidity here, and it's fully enclosed. And for the fabrication part, so in order to take out the backlash, I use 2 screws. So one is offset slightly to the other so that you can adjust it, and it takes out the entirety of the backlash of it. So, and the one thing I was struggling the most is with spindles. You can't get a very small, accurate spindle. It's very difficult to buy them. It's very difficult to get them. So I made a very friction drive spindle. Here you can see this is a bit holder. It holds a bit. It has a small Allen set screw, and this is kinematically locked to the body. So it is made using a lathe, and this is the entire thing. This is the only precision part you need for the entire machine. So here, this holds into a 3D printed bit holder, which you can fit directly into it. So this is like a very easy tool changer. You can take one module out, put the other one in. So it's very easy to switch between the 1x8 and 1x16 and the 1x32. And for testing, so this is the part milling it out. I did some calibration on that. Because it's a friction drive, it generates heat. So I tested with the thermal camera. It doesn't go above 60 degrees Celsius, so it should be okay. Then one of my students made a board for the controller for the entire machine. His name is Fahim, and he built this entirely wireless CNC controller board, which works out of an ESP32. And I'm using that. And this is one. Yes. So we got this machine to Bali. It is there. We can fit in the airport. Nobody stopped me there. And here, the most important, this is the machine sitting in the lab. The most important thing is the kit. Yeah. So the kit, this is the entire parts of the machine. So if you're a fab lab, all you need is this thing. So in like staying in true with the goals of MTM, this is the only specialized component in the machine. Just everything you can print or buy. Here, the only thing is the lathe, small part for the lathe, and the part for the flexure. So I was really happy that one of our students got to use it, and I forgot to make a manual for it, so he figured it out all on his own, and he made the first documentation for it. So after
That's
doing
great.
the math for it. Yes, so he's
Okay.
getting good results. Yeah.
Okay, thank you, Rahul.
Thank you.
So let me take back over screen. Then, see, I don't recall if Sonam and Zena were able to join. Is Bhutan on? If not, these were two Fab Academy students in Bhutan, in the Bhutan Super Lab, developing machine building there. This was one of their machines. And then this was an interesting machine to slice recycled bottles and then extrude them into printer filaments that they then were able to print with. So that's Sonam and Zena in Bhutan. And then Hiro Kazunari, are you on in the Fab Academy? Let's see, I think I need to reload this page. In the Fab Academy, just in passing, for her homework, Hiro mentioned doing her work on this large format machine made in the West Harima Fab Lab. Hiro, are you on?
Yes, this is Hiro, and this is the developer of this original CNC machine, Kazunari Takeda. And he is the founder of Fab Lab West Harima. And we made original CNC machine by ourselves, original design, and produce and purchase the parts and modeling original parts and 3D printer. And we made this CNC machine by themselves. Developer is 3 person and all engineer, but it was first challenge to 2020. We made the first CNC machine.
This is very impressive. Can you give us some background? This looks like a sophisticated design with a lot of experience. Can you give us some background on the people behind the machine and how this project came about?
Actually, first, initially, they want buy shopbot, but the plan is stopped by because to save the money and then the founders think he can make by themselves, but when he sees the shopbot, he worked as an engineer a long time, and make many devices, and he had many experience, but it was first time. How you think you can make?
Okay, thank you for joining us. Links here to everything. It looks beautiful. So we're just up to the hour. I adore everybody who presented in all your projects, but there's sort of a but, which Jake kind of alluded to, which is there's a notion of standing on the shoulders of giants and standing on the toes of giants. And the challenge is many of the projects you saw reinvented everything. And so we have multiple projects reinventing everything. I'm interested from all of the machine builders, what are your thoughts on sort of a synthesis of everything we saw in the last hour?
I think we need to define layers and interfaces and then have a platform to share our stuff.
Okay, Nadia?
We collaborate sometimes. We're trying to control Jake's machines from our from our software. We try to build other people's stuff.
Mm-hmm.
I think it's happening. I think it's hitting like critical mass. One of the things we've been thinking about is if we should set up like a monthly, just like machine club, sort of informal 1 hour on Zoom, which I think makes sense to do. Maybe after this we'll send an email. And,
we nominate you as our fearless leader, Jake.
What's that?
We nominate you as our fearless leader.
I'm not sure. I would nominate you, Nadia.
I already nominated you. The motion's on the table. You can't.
I think it's been seconded, Jake.
But I'll do it.
I think that's a great idea. This is one recitation, but I think if you did like a monthly, I don't know what you would call it, but a monthly get together of the machine builders just to compare notes, I suspect there'd be a big quorum that would want to do what we just did once a month.
I was doing it with Rahul for a while and Jojen as well in Kerala, and it was awesome to see their progress.
Let's see, Jason is asking on going on a tour. I think all of these machine builders love showing and talking about the machines, and roughly I think all would be happy to see them. Ricardo is noting there's an open time in Fab Academy on Saturdays that works great, so a global open machine time.
In response to the tour, I was also a Fab Lab nomad, so Jens and I both did it, and one of the first people I met on my trip was Jens. I just bumped into him in Oslo, like the very first place I went. And that's definitely something that has probably led to me being here now talking about machine building still.
Let me underscore that these were impressive. Roughly nobody who presented is a trained professional, meaning none of these people were formally trained to build machines. All came in like you and discovered.
Wait, what were all the things I learned from you then? Unprofessional machine building?
Well, no, but outside of the canon, there's other parts of campus where you learn the canon of how to do this, and this didn't come in that lineage. So this can be you. If any of you are excited, these are all open designs. Increasingly, they have supply chains. For me, Fab 2.0 means open designs you can make in a lab, but also with supply chains to help with fulfillment. So you can make one machine or you can make lots of machines. And what's emerging that I'm encouraging is the stack of the super labs have things like Zuns and EDMs and these $100,000 machines that let you make the parts of the $10,000 machines. And then with the $10,000 machines, you can make the $1,000 machines. And I guess with the $1,000 machines, you can make the $100 machines.
I think it's also worth noting, I'm not sure if we covered it, but manufacturing as a service has sort of exploded. So lately, even though we have access to a 5-axis machine at the lab, when I want CNC milled aluminum parts, I just send them to, there's like a list of vendors I can post somewhere. And they come back inside of a week and a half, and they're surprisingly cheap. And also what exists is companies like Send, Cut, Send, where if you don't have a water jet, you can send these companies a DXF, they'll laser, metal laser cutter out of aluminum, whatever parts you'd like, and send them back to you. So I think in terms of like bootstrapping capacity, Jubilee has a bunch of machine parts in it. Clank doesn't, but it seems like that actually wasn't a very important constraint. And for things like CNC spindles or things where you really need performance, looking at those for routes into building machines is maybe an interesting thought.
So maybe we could call it MOM, the Machine of the Month Club.
No.
No? Okay.
Also, it's not good to call things a machine of the month. That implies that we should have new machines every month. But actually, what we want to be doing is having the same machines over and over again every month.
Maintenance
item. I'll leave that up to all of you. Jason, you'll see all of the machine builders are chiming in that they're happy to host machine nomads. So again, this is to inspire you and challenge you. Class Wednesday is going to descend into hands-on intro machine building, and then a 2-week cycle of machine building. And then all of this will be on display in Bhutan and beyond. So we're a little over the hour. Fabulous job. I just adore what you're all doing, and it really is going to change the world. And in fact, as we sign off, I note, like I see Dan, who's made beautiful machines. There's a number of other machine builders. The machines.fab cloud.io right now is just a list of links. Eventually it'll grow beyond that, but I want to use that as a central portal to keep track of all of this. And so with that, thank you, and I will stop the recording.